So KSP, the key with all of these, right? These are our notes, the solubility equilibrium. The key with all of these, actually, you know what? We're going to come back to page 34. I'm going to start on page 35 because I want to do, this is a good practice problem, introduction. The first thing you always do is what? I don't have a pen.
Write your case expression.
Write your equation and your expression. Yes. So for nickel hydroxide, for the precipitate, and you always start with what state of matter?
Solid.
Solid to the ions. So nickel hydroxide is what we're doing. This apparently is frequently used in electrical car batteries. All right, show your solid, and we split it into nickels a +2 and 2 hydroxides. I'm going to put a parentheses just so you don't think it says 20 H's. And I will get a pen at some point. Oh, maybe one of these black ones will work. Find out. You can show your aqueous, but it is always solid to aqueous. Always start by writing your equation and then also write your KSP expression. So we ignore the solid, so it's just going to be the ions. And this is really the key to these. It makes it much simpler. So the 2 does not go inside the parentheses. The 2 becomes the exponent. This is back to some of the questions that came up during office hours, which are really good because I know what to expect. All right, so always start every problem like that, and then we have to see what information. The equation is there because then we plug in what pieces we have, and then we're going to plug into our KSP. And to look up KSPs, because you get to do this a lot in your study set, you go to the end of your notes, and there's those 2 pages of KSPs, and we would find nickel hydroxide, so 2.8 e to the -16. Is that what you guys have in yours? We're gonna hope that. You need to use this chart because I suddenly started writing other numbers here. Oh, I know why I have those numbers. We know the nickel because that is the 0.010 molar. The hydroxide is my unknown. If you're not given either concentration, so if you're given neither, so it just says, what is the precipitate? Then this would be X and this would be 2X. But if you know one of them, in this case, the nickel, the other one is just your unknown, it is X. That is the most asked question. I guess because it's not a question in my head, I don't know better how to explain that. This is saying that you're starting with a solution that is purely nickel hydroxide down here, that all you have is nickel hydroxide. There's nothing else floating around in there. There's no floaties, there's no other ions, and so they must be stoichiometrically related. Here, they are not stoichiometrically related because you have something else. In this case, you have nitrate. It is floating around because nitrate is always a spectator, but because you're mixing them from 2 different ways, they're not stoichiometrically related. I don't know if that helps to explain, because some of you, a couple people came to office hours yesterday, and that is always the piece that is most missed. So since we know the one, the other one is just X, and then we plug into our KSPs. This is back to a question that was coming up. So it has to be molarity that we plug in, and this is x squared. And that's why you always state the KSP, so you remember to square that. If we did it, if I'd asked the question, which I wish I did, and if I remember after, I'm going to make this question there. This here, we had only nickel hydroxide, not nickel nitrate, and this would be where we have x, and the 2x is squared. So this is the 4x cubed question. And yeah, because the 2 and the x get squared. All right, so you solve for x and identify that x in this case is our hydroxide. It's really helpful to say what your x is, or you can write what your number is for x and we can write it in that setup. So right, we would divide by the 0.01 and then take the square root. I don't need to see that algebra. You can, if you're comfortable to do it like without showing it, but you can absolutely show that if that helps you. So it just has to deal with how we learned algebra. Yeah. You actually learned algebra back in kindergarten, and then you got distorted, and then you had to relearn it incorrectly. So that's part of why I homeschooled Joey. So Joey thinks it through like I do. All right, 1.67 e to negative 7. The units are moles per liter, and I think it's helpful to say what kind of moles. So either here or in both places. So this is moles of your hydroxide per liter. And then what's the question want to know? It wants to know the pH. So there's no need to double or anything. We're going right into pH. That's my hydroxide negative log of your X is going to be your POH. And then you just change it to pH. And that's where I get the 7.22 is my pH. So questions. Okay. Solve this one also and find the pH. Just for the heck of it. It's a good one. So this is like we would have a saturated solution. It doesn't tell us how much is in there. It just says you have a saturated solution of nickel hydroxide. That means there's nothing else there. So what's the pH? You're using the same KSP because it's still nickel hydroxide. I have for my X 4.12. So comment for you all. A couple of people turned in their worksheet early, which is really good because then I know what comments make for all of you verbally. So KSPs are really approximate. You can round at the very end to 2 sig figs if that's what you want to do. pH, a reminder, this number is 2 sig figs, 7.22, because it's a log function. And once you do a log function, only the numbers after the decimal count towards sig figs. So 7.22 as a pH is 2 sig figs. You need to always give your pHs to 2 decimal places, at least. All right, when you solve for X doing KSPs, please keep 3 sig figs. You can keep 4, but if you round to 1, it's gonna create issues where your numbers are gonna always be different. And that, for some of the stuff we're gonna be going to, can make enough difference. All right, this X this time though, is the nickel. So this is moles per liter of the nickel. And this is this was a question, well, several of you are asking. This is the opposite of question number 2 on the study set. So on question number 2, we know the hydroxide. So if we knew the hydroxide, the nickel would be half of that. In this case, we know the nickel. To do pH, we need the hydroxide. So we would just do 1 mole of nickel to 2 moles, or you can just say hydroxide is 2x. That's going to give me my hydroxide, and then so basically we're doing negative log of 2x. That will give us our POH, and then you can change it to pH. Questions with that? All right, for this one, I got a pH of 8.92. Hopefully somebody else got that, since I just kind of made up this question off the top of my head. I am going to ask this question while you ponder it. This would be part A and B. So here we have nickel nitrate added to our solution. Here it's just nickel hydroxide. Why are the pHs different? Like that extra bonus point question on your worksheet. Anybody? Oh, if nobody gets it, then it gets to go out there into the cloud for anybody to email me and answer once this posts. So that can be you guys too, that once you figure out why and can explain why the pHs are different and what happened to the pH. Does somebody else get my 8.92? This one should be higher.
Yeah, I got that.
Okay, you can ponder it. The answer might come up when we go on the next page. All right, that's the basic idea of how to do these. You write your equation, you write your KSP expression, and then you figure out if you're not given anything but that solution, they're stoichiometrically related. If it's a mix, something else is being added, you can cross out your spectator, and so that's our nickel. All right, let's go back a page, page 34, and we did the first one at the top, simultaneous equilibrium. These weren't on the worksheet and quiz, and sorry, study set and worksheet today, but it's on the one for tomorrow. So you see the equation. The one we did yesterday or Monday, sorry, we actually wrote it all from scratch. Usually you're going to be given the equation, and it's a net ionic equation. It left out the spectator, which was probably sodium. So instead of showing the sodium iodide, the sodium doesn't matter because it's just swimming around. It doesn't change anything. It doesn't even affect the pH. So what we're going to do is we're going to write the 2 half reactions. So we start with the silver chloride as a solid, and we'll go to its ions. And then we also pull down on the product side in the second equation, silver iodide as the solid. So the top one, and it doesn't matter which one you show first. So the silver chloride is starting as the solid here. So it's going to break into silver ion plus fluoride ion. This is bringing back from previous memories. So if we were in class, people are doing practice problems, and I'd just be going around pointing to like 80% of your paper saying, you got to show the charge. You got to show the charge. And then there'd be the ex-Marine in there saying, I'll make it real pretty for you for the real thing. Make it real pretty for me now. Always those ex-Marines who do that. I'll make it real pretty for you when it counts. It always counts. All right, this one, the solid's on that side. So we'll write silver ion plus iodide ion. And then we go to the chart. So those charts are really handy. Make sure if you don't print, at least have them handy on your computer. So the first one is the KSP because it's solid to ions. So we look up the KSP is 1.8 e to negative 10. All right. For the second one, how is it related to the KSP? So I flipped my equation when you flip the equation,
It's to a power of -1 of negative.
you can say -1 if you want. So we can say that the KSP would be, if you look it up, 1.5 e to -16. I just do it all in my calculator. This would be to -1. So, and then you would multiply the two of them. The other way you can do it is you could also just say the KSP for the silver chloride and divide it by the KSP for the silver iodide. So taking this one, so you can either multiply by it to the -1 or just divide by them. The answer does come out, well, why don't we just do it? So 1.2 e to the 6. No units, it's a K value. So that's our K net, or just K. You're going to be asked what that number means. So anybody know what that number means? K is greater than 1?
It means product favored.
Yeah, so we're looking, is K greater than 1 or less than 1? So whenever you solve for a K value, and I'm like, what does that mean? So it's product favored, meaning what precipitate formed?
Silver iodide.
Yeah, so it's moving in the forward direction, silver iodide. So silver iodide precipitates. Yeah, questions with that? There's another way to do it. The one on the study set and the worksheet is where we're just comparing KSP, but this is given the equation. So we're going to take it to the next step, which is the complexions. So there is actually space here, not like saying, hey, how's your complexion today? There is a space. And so a chemist would read that as complex ions. But I've learned from my students, they all think I'm talking about complexions with that. So that's where that picture came from. All right, this is the idea that many of the cations, so a simple ion, it's more, what's the difference? There's two basic types of ions. A simple ion is all the ones we've always been talking about. So sodium, +1, calcium's a +2, iodide or chloride, those are simple ions. A complex ion is where we have a cation and it combines with ligands. And so it combines with the other things. Mine has a typo. I don't think it's on yours. That should have a 6 there. And this should have some number. I'll just leave it for now. We'll make it a 4. So these, the hydroxide or the ammonia or whatever, these are called ligands. And there's another set of notes, which we may or may not do today. We'll talk about that in a bit. We have to do it before Monday. So those are ligands and they combine with it. So you get this big complex. So like the iron, I'm just going to show you a picture and we'll see them when we get to the notes. So this is the other set of notes. So copper is the ion and it's attracted to the NH3. And so this whole thing is a complex ion. They're all connected. Or here it's showing the MT just means metal. And it's got, this is, I'm pretty sure EDTA. And so it's used actually in medicine, environmental medicine, as chelation therapy. It's also used in all the socialized medical countries. Chelation therapy is used for heart disease because the #1 cause of heart issues is calcium ion buildup in the arteries. And so they do chelation therapy to pull the calcium out. All right. So that last page of your notes has another chart and they are KF. So if you have your notes and you look at that last page, the 2 pages before it are Appendix J for Joyce, your teacher. And those were all KSP values. This last one is Appendix K for kangaroo, and they are KF values. They are, the F stands for formation. So they're formation constants of complex ions. Exactly what the chart says it is. All of these values, if you look at them, KFs are always greater than 1. They're always quite a bit greater than 1. What that means, you want to make these. These things want to be formed. They love binding to their ligands or ligands, depending on which side of the Mississippi you come from. All right, so let's write a formula for it. So that's another chart, and it is called F for formation. So here's our complex ion. That's our complex. This is our precipitate. So hydroxides precipitate, that's a KSP. So when I said write the KSP, you're going to write the solid, copper hydroxide, to its ions, double arrow. Everything this term is the double arrow, except titrations, right? But then they become a double arrow. So that's our KSP, and we can look up its value in the chart J. KFs are forming. So the difference is the complex is what you're making. So the complex is always shown as the product. So KSPs are solid going to aqueous. KFs are going to be whatever you have over here making the complex. And so what we have is going to be the copper ion and then the ligands. The ligands can be, they can be neutral like NH3 as far as no charge. But we have 4 NH3s, which actually is a gas. And we would form this. Complex ions are always aqueous. So you can show the aqueous, you have to show the charge. The +2 is because the copper still has a charge. The nitrogens are attracted to the copper. And again, when we get to that point in the notes, which may happen today, we'll see. And then we'd look up the KF value for that. And all right. So you can trust my numbers. I have 1.6 eats -19. When I look up the KSP, copper is under copper, not Cooper. And then KF, we look up the KF and we get 6.8 e to the 12th. Now, I did not flip any equations around. That is how KF is written. See, we just multiply these two. So our K net is KSP times the KF. Now, if I write my net equation, I just add these two equations up. One thing cancels out. What cancels out?
The copper?
Yeah, the copper ion, because it's on the left and the right, it's on the product and reactant. So the copper would cancel out. And so our net equation would be the copper hydroxide solid. Always state the solid. The NH3, and the NH3, I'm putting it as a gas, but in all honesty, some books show it as aqueous. Some places will show it as aqueous. That's not a big deal for this. This question got eliminated from your notes because it ended up confusing students some. I want more that you get the big picture here, and we put our two ways. We have the complex ion, which still has a charge, and our 2 hydroxides. And I leave, again, I mentioned this, when I'm showing the ions, because you have to show the charges, I leave off the aqueous, but these are both the aqueous. You can show them, but it just seems to then confuse students with the subscripts, especially because you guys are all like looking at the screen and writing down. If we punch that in, we're going to get a value below 1. But we can punch it in while you guys are all writing. Never actually done that before. In like 25 years. It's awesome. All right. So our K net is like 1.09 or 1.1 e to the -6. So all I did is take the KSP times the KF. So I'm going to ask it again. What does that number tell us?
It's reaction favor. I mean,
So-
more.
K is less than 1. It is reactant favored. So keep going, Major. What was your next piece? Because I want one more piece. Go ahead.
Is it just that there's no more PPT? It would be more.
No, we're going towards the reactant. So look at our equation. The PPT is on the reactant side. So if it goes
More precipitate.
reverse, it's going reactant, it's going reverse, so precipitate forms. So the question would have said, it would have asked actually, did the precipitate dissolve? And you would have said, K is less than 1, precipitate formed. If K was greater than 1, it would have gone forward and it would have worked. Now, according to Le Chatelier, we could make it dissolve. So any idea how we could make this dissolve? Look at your equation. Well, Le Chatelier is, and again, I don't say his name correctly. Some of you yesterday mentioned him and said it much better with a French accent. But if we added more ammonia, if we added more of the ammonia gas, we could force this in the forward direction. So if you keep adding the NH3, and that was actually in the very first lab, that Le Chatelier's lab, there was the one page about complex ions. And I don't think I did actually this experiment, but if I kept adding something, we can force it because they really want to form their complex ions. And so we need an excess, like this is a power of 4. We need a huge excess of NH3. And if we can get enough excess of NH3 there, the copper will preferentially form this ion. So, all right. Questions? So 2 types of reactions. One is where they're both solids. If they're both solids, you're using KSP. If you have a solid and then this complex kind of thing looking, then it's like this problem. All right. I think the homework set for tomorrow, the study set, I think the second page has a couple of these on there. You guys are going to do great with it because you're an awesome class. By the way, I meant to say this at the very beginning. So well, I guess I should say, first of all, I'm very bummed that nobody dressed up as a mermaid or an octopus. Joey decided I was an octopus today. But tomorrow, we're doing a review for the celebration. So you have a chance. You can dress up as a mouse. You can dress up as an octopus. You can dress up as a mermaid. Captain America is not part of this, so that doesn't work. What else do we have? You can dress up like with a towel around your head. We're doing complex ions eventually here. All right. The thing though that I wanted to say is I like woke up this morning and I was just in the most delightful mood of gratitude because you guys really, every single person, all of you nailed your presentations. Those of you who've been with me, that was actually the most pleasant because I've got to see the growth of you and just how casual you all were and just like chilled out and talking and all of you like interacting with each other. I had wanted to do 3 presentations with this class and I was like, you know, I have to teach some chemistry. But the reason I do those live that you guys have to do that is my attempt to try to get you to interact with each other on this Zoom. Devin and I and Major reminisce about the good old days when we were in lab, and it wasn't so much about mixing the chemicals, it was you got to know your classmates. And that's what you guys are missing out on, with or without masks, it doesn't matter. All right, I think the only page we have left is page 36. We did the first one, so we have 4 problems here to do. So we might be able to get to this. All right, this is a page that's reaction quotient. These are not on the study set for today, for Wednesday, so that's study set and worksheet 7. These show up on study set and worksheet 8. and those reaction ones and the pH ones. Oh, some of the pH ones are on today's. And this, you're going to know it's a Q problem because it's going to say, yeah, you should never lick the paint, no matter how hungry you are, because of the whole lead poisoning thing. But you're going to know it's a Q problem because of a couple things. One, it will say, does it precipitate form? So the question's not saying how much formed, how much dissolved, what dissolves first. It's just saying yes or no. And we don't see those equations. So what's the first thing you're all doing? Hopefully you're all doing. I can only see 3 of you.
Let's write the equation with the question.
Write the equation and write your KSP. So we're doing it for lead iodide. Starting with the solid. And we break it into the ions, showing the ions with charges. And again, because half of you had somebody else for your chemistry, I write it as +2. You can write it as 2+. I really don't care. No one really cares except somebody, but we'll let them worry about those things they care about. All right, and then you write your KSP expression, and it does help to do it. Well, that's just how I do it. Ions, you have to show the charges. Here it's iodide squared. So whenever we plug into that, we're going to solve it as a Q problem. There is another way you can solve it, but then you have to think, and you're going to have to explain why the answer. It's going to actually usually ask you, does it precipitate form? And then it'll ask you to explain. So we're going to do, when we see that, we're going to solve as Q. So we have, this is the other thing, because a lot of you maybe never saw this. Those of you who were with me, I threw these in 221 because of this term. This is a real unit. I didn't make this up. So it's a little m and a capital M. It's not my typo. This means millimoles. It is such a thing. So if I'm gonna show you, it means 10 to the -3. So that milli is 1.1 10 to the -3 moles per liter. There's also a micromolar, nanomolar, picomolar, femtomolar. And for all of you who keep telling me how much you love biology and you're not fond of chemistry, the nanomolar, picomolar, femtomolar, they're used in biology. So because you're working, when you work with DNA and cells, you're working with really diluted concentrations of stuff. All right, all we have is this. So if this is the amount of PB, and Major just got kicked out, bummer. But this amount of PB, this is the question he was asking me. The iodide is double that. So 2.2 e to the -3. You can stoichiometrically show that, or you can recognize. So again, this is only if all you have, because we only have PbI2 present. There's nothing else. That's going to change on the next one because I'm going to be mixing 2 different things. So we'll worry about that there. And then I plug into my KSP. So you had to double the iodine and square it. Right? So that's my PB. I doubled my iodide and I square it. This is going to give me a Q value because it doesn't say this much dissolved. It just said, did it? Is it? Whatever. I'm so happy my body healed. All right. 5.3 e to the -9. And then with Q's, we compare it to K. So alphabetical, that's how I do it. So I can look smart while I'm a mermaid or an octopus or whatever you want. All right, so K and Q, looks like K is larger because K is 8.7. Oh, there he is. Let's stop talking about him. K is greater than Q. If I had more space, I would actually fit it in there and write it above. But the K is larger, it goes forward. So this is, if you do it by Q, this is the explanation I need. You can just, you don't have to write out a sentence, although you can if you're Peter. You can all write out full sentences. It's beautiful. K is greater than Q, so no precipitate. In this case, the ions are on the product side. So there's no canary orange, yellow precipitate. All right, we'll keep going. So on the next one, we're mixing two things. So the biggest mistake students make on this one is they want to write a reaction with everything. Don't do it that way. We're not going to do it that way. We have a bright green pen. We're going to cross out the spectators. Nitrate is always a spectator. You ignore it. There's only one time we don't ignore, and we're going to ignore the sodium. So sodium, potassium, hydrogen's always going to be a spectator in these problems, and nitrate. There's others. There's like 4 cations and 4 anions, but I'm not going to mention them because I try to stick with sodium and nitrate. There is one time that you do not ignore the sodium. So you do pay attention to the sodium or the nitrate. And that is if I start you with grams. So if I start you with grams, which at some point I do it on the study set today because some of you are asking. If I start you with grams, you have to factor in the sodium or the nitrate because it started together. It's once you put it into the water and it becomes aqueous. But starting as grams, it's a solid and then it's aqueous. So you have to factor it in when you use the periodic table and do the molar mass. And you'll see as you do your study set. All right, so basically this number is going with the carbonate. And this number, that's a micro. And if you print and your printer puts a box here, so if it showed like a little box and a capital M, please realize you can pull it up on your screen, but it means that your printer doesn't recognize the Latin or the Greek. And it's really not going to be happy next week because I use a lot of Greek symbols when we get into these things. This number, the 1.5 micromolar, is the nickel 2. So my question is, and it says that, here's your hint. What is the precipitate? Because that's what we start with. So again, we're not writing a double displacement reaction. Cross out your spectators. You know what they are. We're writing KSPs, which means we start with the solid. So my precipitate is nickel carbonate. So nickel and carbonate. Put your arrows, my solid. The nickel, I know it's a 2 charge. How do I know it's a 2 charge?
The Roman numerals.
Numerals.
Yeah, that 2 is telling me I have a +2. And then carbonate, you can always Google if you don't know your carbonate, -2 or 2 negative. So it is a 1-to-1 ratio. But these are not stoichiometric. We're not doing an X times X problem here because we know each one. So this is 1.5 micromolar. So what does micro mean?
Is it 10 to the 6 or the 9?
Negative
It is 6. Nano is 9,
Nano is
but it's
9.
negative. It's -6
Mhm.
because it's a small number, right? Micro's micro. I think it's smaller. It's like my dog's micro dog. People call them toy size dogs. I call mine a micro. All right. E to -6 capital M. You can show the step, or that's what micro means if you go with the definition. And then carbonate is the 0.60 millimolar. So you're basically dividing by 1,000, or you can either say 0.60 times 10 to -3. I just want to remind you that's like an illegal comment there, but if you can do it like that while you're doing your math because it's not your final answer. This would be 6.0 e to -2. because we'd have to move our place value. You can ponder that either way, or I should write or 0.06. All right, what did I forget to do?
You have to account for the dilution.
Right, the KSP. Yes, and thank you. We're going to do that. Sumner, you are absolutely right. We want to write our KSP expression. I know, and I'm pondering, I didn't give myself enough room to show my dilution. We'll do it over. We'll fit it here. All right. I was trying to show how you can change your millimolar. You can show it, you can change it like that in your head, or you can show the step. And so Sumner is absolutely right that there was another piece of information. And that is that we have 100 milliliters and another 100 milliliters. So this just changed the game of this problem because the volume's changing and we have to factor that in. And so it is actually, he said it correctly, it is a dilution problem. So a way to think about it, and you don't have to write it down like this, but this is how you're going to see me solving. Dilution was M1V1 equals M2V2. So the initial molarity times the initial volume equals the final molarity times the final volume. Kind of like gas laws with pressure and volume, but molarity is aqueous. So basically, you're going to take the molarity times the volume, and then we're going to have to divide by the final volume, which means for the nickel, we would have 1.5 e to negative 6. It has to be molarity. You can write moles per liter times its 100 milliliters over 200. You impressed by my math skills? 100 plus 100 is 200. You can check it on your calculator. Now, quick comment for you. I didn't change to liters. Did I have to? Or why do I not have to?
You don't, because it cancels.
Yeah, if it's because it's that ratio thing. I'm a volume over a volume. If you see that, just you can leave it in milliliters. If you're ever unsure, just change everything to liters. We're gonna do the same. I'm sorry, I wrote my formula wrong. The carbonate, that -2 is inside there. What's my carbonate point? It's gonna be 0.06 molar times 100 milliliters over 200 milliliters. This was much more fun on the blackboard where I ran out of room. All right, and then we should punch that in and get a number. And if you want, some students like to give me what they get for each of these. We're not squaring anything because it was just a 1-to-1 mole ratio, but we have to factor that in. All right, I get a number. This is going to be a Q. So we're mixing them, and we know it's a Q because of how this is worded at the end. Will precipitate form. So you write your expression the same way. Yeah. All right. The Q I get is 2.25 e to negative 10. And then you compare. You'd have to look up the KSP. So the KSP for the nickel carbonate in the chart, you can trust that I looked it up 10 years ago, 6.6 e to negative 9. And we compare them, which one's bigger? They're negative exponents.
The KSP is
Bigger.
Yeah. So K is greater than Q, goes forward, no precipitate. So I'm going to pause this. You guys are going to see what you can do. You can take a break for a couple minutes, or you can try these, or at least figure out what your precipitate is, write your equation. So cross out your spectators first. And okay, I'm going to pause this. All right, I'm back. So we're going to try these problems. Behind me on the board is I'd sent out an email before the presentations. I read some of your meditation papers, which have all been really delightful. I'm like really amazed, but I sent an email that said, if you keep meditating, doing your gratitude or whatever for until the end, yeah, there'll be bonus points, along with if you made a healthy diet change. And if you're like, yeah, just keep doing it. And I will have office hours on Friday. We'll talk about that tomorrow. I am going to do the review on Thursday at both the 1 o'clock time and then in the evening time. So we'll be doing the practice for Monday is the exam, and we'll talk about all that tomorrow. All right, let's finish these, and then we're going to move into complex ions. So this is my barium, the 0.01, and it wants to know how much of the sodium sulfate. So really what I need right now is the sulfate and the barium. That's my precipitate. So that's one of the key things with these problems. If it's two things mixing, figure out what the precipitate is. And again, the trick is I pretty much always pick nitrates and sodium or potassium that you can cross out. So you can just go straight to barium sulfate is your solid, goes to its ions, so barium and sulfate, shown as ions with their charges, and then that's the KSP we will be looking up. The ions are ions inside their brackets. The good news here is you don't have to deal with stoichiometry. Teacher just has to find her note. All right. And we know the barium, which is 0.010 molar. The sulfate is my unknown because it's asking how much. And so you just look up your KSP value in the chart, which is 1.1 e to the negative 10. And that's going to be 0.01 times x. All right. This is one of the ones, if this had been two sulfates, that we would not do a 2x. So again, if you know one, the other one is just x. We solve for x. So x is going to be, do it down here. So x is 1.1 e to the negative 8. This is moles per liter, and this is of the sulfate. So questions to that point: write your equation, state your KSP, figure out what information you have, we plug in and solve. This is not a Q problem because it's asking a how much. It's asking for a number. So again, Q's are, do you see a precipitate, not how much precipitate. On the next one, see the difference, what mass precipitates. So I'm going to show you how to do that. All right, this stoichiometrically, 1 mole of sulfate in the sodium sulfate. So there's only one sulfate in sodium sulfate. This is what I was trying to say before. So I ignored the sodium because it's not part of the precipitate, and the KSP is all about, right? We're looking at precipitate to aqueous. The KSP is about how much is soluble of the precipitate. But when I'm going back to how much, meaning I would phrase it as how many grams is what we're going for. I do have to factor in the full compound. And I did mean how many grams. So 1 mole of sodium sulfate is 142-ish grams. So 2 sodiums, the sulfur, 3 oxygens, and it doesn't look like it gave a volume. So, all right, so we get an answer which is 1.6 e to the negative 6 grams per liter. And then it will say, please give your answer to the appropriate metric prefix. So that's kind of what I'm forcing you to learn in this next week, is your metric if you didn't. have a nice metric table, however you learned, and you should find that -6, kind of back to something that a lot of people think of micro as 10 to the 6th, but micro is a small unit. It does mean 10 to -6. So you can show the step, or you can simply say that this would be, sorry, I have to write it over here, 1.6 micrograms per liter. You can use that mu like I had up here. With grams, they usually do write mcg just because they want to make sure people can read the handwriting. So you can also write the funky. So 10 to -6 grams is 1 microgram. There's 1,000,000 micrograms in a gram. You can ponder that. You should be feeling more comfortable with metric, or just work with it. All right, barium fluoride is an iridescent gem. And it gives us a mass, it tells us a volume, and it wants to know how much precipitates. So first thing you always do is write your equation. So barium fluoride, barium is one of the earth metals. So the earth metals love to precipitate. So barium plus 2 fluorides. State your KSP formula. Show the charges inside the parentheses. The 2 now is the exponent. And so again, if nothing else you got from that first lecture that I posted, other than, and this is what everybody gets, is that you at least got this today. You're really 90% of the way there, because this is the key. Now, we're not going to do anything with that 1.111 grams, because it doesn't say that's how much dissolved. It just says it's placed in there. What KSP is how much dissolves. So this is X and this is 2X. All right, we'll look up our KSP. Oh, this one's not too bad. 1.7 e to -6. And we would have X and then 2X squared. So this is a 4X cubed. You can go right to that. So if you have X and 2X squared, and we solve for X, you should get 0.00752, and that is moles per liter, or 7.52 times 10 to -3. It is moles, it is X, it is moles of the barium. So again, the only thing we have present is the Frank-Dixonite, which is barium fluoride. And so this is X and 2X. They are stoichiometrically related. My mole to mole ratio, it is 1:1 to get to the barium fluoride. And I want a mass, so I am going to factor in the mass of the barium fluoride. So barium and 2 fluorides, 175.3. That's that whole compound. And we do need one more step. So my moles canceled. I have grams. I do have a volume on this one. I did not on the previous one. Well, everybody's Wi-Fi must be doing wacky stuff today. So the milliliters, you can just do that trick, divide by 1,000 and make it liters. So I ran out of room, so I'm going to do that trick, 0.777 liters. And that's wonderful. So that way, when you're in physics or whatever class next year, you're comfortable changing milliliters. All right, we get a number, which is 1.02. We're not done. It's not that there's a mistake on if I put an answer there. What does the 1.02 mean? I did put a couple names on the board, partly because I was impressed by Sumner's comment that I had to factor in the dilution.
It's the BAF2.
What about the barium fluoride? You're right. It is. It is how much dissolved.
Yeah.
Whenever you solve for X, that is how much dissolved. Are we done?
No, we're looking for the PPT.
For the precipitate, yeah. You know, you just gave me an idea. I'm still, this could be another bonus besides the one when you figure out that pH question I asked earlier. You can all email me with your answer, even those who are watching the video later, so you can all get up a bonus point added to your worksheet. But the Peter, Paul, and Perry precipitate, this definitely has to be part of the alliteration. That was me just pausing to see if anybody sees what we have to do. There's one more step.
Subtract the mass dissolved from the original mass of barium fluoride.
So this mass, the only time we're going to use this mass, so you have to label it. We're going to go over here. You can number your steps, or you can do the arrow thing. So I have 1.111 major. How many ones do I have? Looks like 7.
8, 7.
Okay. This is grams of barium fluoride, initial or total or added. So you want to label it. Same like I am. You've got to label it to get full credit. We're going to subtract the 1.02 grams that dissolved. And whatever you're left with is your precipitate. You can just say PPT. Just a quick comment. Oh, so we'll get a small number, but it's not too small. So 0.091. Is that right? So by sig figs, it should just be 0.09. That's why I knew I had something off. Or 90 milligrams or 9 centigrams, however you want to say it. That's your precipitate. Sometimes it's even smaller. By sig fig rules, you can't go more than 2 decimal places. If you're somebody who's like, I want to get the sig fig rules. So 0.09 grams precipitates. And again, if you want, you can then change it that 10 to the negative 3 grams is a milligram. So I don't know what I put as the answer. So 90 milligrams precipitated. If I want the answer in an appropriate metric, again, you could do 9 centigrams or 90 milligrams. We're just getting rid of all the decimal places. A quick comment, and then we're going to move into complex ions, and I'll talk about this more tomorrow, actually. The next lab, there's something I talk about, and it is, there's always 2 parts to a solution. There is the precipitate, which is the solid, and then the stuff that's left behind is called the supernatant. So I talk about the labs, the last 3 labs are really fun. They're really fun in lab. But I'm going to stop recording, and then I'm going to start up again. All right, thank you. Goodbye.